Welcome to the deep dive, where we cut through all the noise and get right to the heart of it,
Right to the juicy bits.
To the juicy bits, yeah. Today we're diving into fusion power.
Ooh, exciting.
Yeah. Have you heard about this? It's been in the news a lot lately, this idea of harnessing the power of the sun. Sounds pretty sci-fi.
It does sound very futuristic.
But we wanted to dig in and figure out what's real and what's hype. So we got a few things to help us out today.
Okay, cool.
We've got a couple Wikipedia articles, one on fusion power and another one on heat fusion.
Okay.
We also found this website article called In a Few Lines, all about this thing called ITER.
ITER. Interesting.
Yeah, it's a big project. We'll get to it.
Yeah.
And a science article, too, called Inside the Tokamak, Scientists Crack the Code to Stable Fusion Energy.
Wow, they cracked the code.
That's what they say. So our mission today, by the end of this deep dive, we really want to make sure you understand what fusion power is, how close we are to actually using it, and what the good and the bad are.
Sounds good.
I'm ready. Let's do it. So first things first, what is fusion power? Why is everyone so excited about it?
Well, in a nutshell, we're talking about recreating the process that powers the stars.
Whoa, hold on. We're trying to build a star.
Not a whole star, just the process. It's called nuclear fusion, and it basically involves smashing atoms together at super high speeds to release a huge amount of energy.
So like atom smashing. Okay. But how's that different from what we do now with nuclear power?
Ah, good point.
Yeah.
That's nuclear fission, what we use currently, and that's all about splitting atoms apart.
So fusion is smashing them together, fission is splitting them apart.
Exactly.
Okay, I got it. But why is fusion so much better? I mean, fission seems to work all right.
Well, fusion has some serious advantages. First off, way less radioactive waste, especially the really nasty, long-lasting kind that we have to worry about with fission.
So it's much better for the environment.
Much better. And it's inherently safer, too. The reaction can be stopped much faster if something goes wrong, unlike fission, which can kind of spiral out of control.
I see. And what about fuel? Where does the fuel for fusion come from?
Well, it depends on the type of fusion reaction we're talking about, but in many cases, the fuel supply is practically limitless.
Okay, so we've got tons of fuel, it's safer, and it produces way less waste. Fusion sounds amazing. So how close are we to actually making it work? Can we build a mini sun in our backyard or something?
Haha, not quite.
Yeah.
It's not that easy. We need to create conditions here on Earth that are similar to the core of the sun. We're talking about temperatures of millions of degrees Celsius.
Millions of degrees. That's insane. No wonder it's taking a while to figure this out. So how are scientists even trying to do this?
There are a couple of main approaches. One is magnetic confinement fusion, where they use super powerful magnets to hold this superheated material called plasma inside a donut-shaped device called a tokamak.
A tokamak, like a magnetic bottle for a mini sun.
Exactly. And the other approach is inertial confinement fusion, where they use high-powered lasers or particle beams to basically crush a tiny pellet of fuel and trigger a fusion reaction.
So we've got magnetic donuts and laser beams. This is wild. It says here that there have been over 200 experimental tokamaks built around the world.
Wow, that's a lot of donuts.
Right. So if we've been working on this for so long, why haven't we cracked it yet? What's the holdup?
It comes down to energy balance. For fusion power to be practical, we need to get more energy out of the fusion reactions than we put in to create those extreme conditions.
So it's not just about making fusion happen, it's about making it efficient.
Exactly. Think of it like trying to start a bonfire with a single match.
You need a lot of energy to get the fire going.
Exactly. And scientists use something called the Lawson criterion to measure how close they are to achieving that energy gain.
The Lawson criterion? What's that?
It's a threshold that tells us if we're producing more energy from fusion than we're losing to the environment.
I see. So it's all about getting more energy out than we put in.
Right. And the key metric they use is something called the triple product, which combines the density of the plasma, the temperature, and how long they can keep it contained.
So it's a balancing act.
Exactly. We need high density, high temperature, and we need to hold it all together long enough for fusion to happen. And to really tackle this challenge, scientists from all over the world have teamed up to build this massive project called ITER.
ITER, that's that giant tokamak being built in France, right?
That's the one. It's the culmination of decades of research, and it's designed to show that fusion power can actually work on a large scale.
It sounds like a big step forward. But even with all this effort, there are still people who are skeptical about fusion. And I get it. It's been just around the corner for a long time.
Yeah, there have been setbacks for sure, and there are still some challenges we need to address.
What are some of the potential downsides to fusion power?
Or remember those neutrons we talked about earlier? They carry a lot of the energy released during fusion, but they also present some unique challenges.
Uh-oh. That doesn't sound good. But we'll have to save that for after a quick break. Don't forget to like and subscribe to The Deep Dive for more mind-blowing explorations. We'll be back in a flash.
Yeah, those neutrons can cause something called neutron activation.
Neutron activation. What's that?
Basically, when those high-energy neutrons hit the materials around the fusion reaction, it can make those materials radioactive over time.
Oh, so even though fusion is supposed to be cleaner than fission, we still have to worry about radioactive stuff.
Yes, unfortunately, that's one of the challenges. And that leads us to another issue, the fuel itself.
Okay, what about the fuel?
Well, the most promising fusion reaction we're looking at right now uses a mix of deuterium and tritium.
Deuterium and tritium.
They're both isotopes of hydrogen.
Isotopes. Now I'm a little rusty on my chemistry. What are isotopes again?
Okay, so all atoms of an element have the same number of protons, right? That's what makes them that element.
Yeah, like hydrogen has 1 proton.
Exactly. But they can have different numbers of neutrons, and these variations are called isotopes.
Okay, so it's like hydrogen with extra neutrons.
Exactly. So deuterium is pretty abundant. We can get it from seawater, but tritium is much rarer, and it decays really fast.
How fast are we talking?
It has a half-life of about 12 years.
Half-life of 12 years. That doesn't sound very practical for a fuel source.
That's why researchers are working on breeding tritium within the fusion reactor itself.
We can make our own fuel.
The idea is to use lithium, which can be bombarded with neutrons to produce tritium.
So we'd be creating fuel as we go. Pretty
Yeah.
clever, but is it really possible?
It's a big challenge. We need to figure out how to produce enough tritium and then capture and contain it efficiently. And, tritium has a bit of a track record of leaking from nuclear sites, even with those fission reactors.
Yeah, I read that tritium has leaked from almost 75% of nuclear sites in the U.S.
That's right. So there are a lot of obstacles to overcome.
Yeah, between creating those crazy temperatures, dealing with the neutrons, and now this whole tritium thing, it's starting to sound pretty complicated. And expensive, I bet.
Yeah, the economics of fusion power are definitely something to consider. Fusion power plants would require a huge upfront investment.
Like, how much are we talking?
Well, that giant tokamak we talked about is projected to cost tens of billions of dollars.
Tens of billions. That's a lot of dough. And then there's the cost of running and maintaining these things.
Exactly. So it's a big gamble with no guarantee of a payoff.
I can see why some people are hesitant. But then we have all these headlines about fusion breakthroughs. Like this in A Few Lines article, in that Science article about stable fusion energy, they make it sound like we're on the verge of a fusion revolution. What's the real story here?
Well, there has been some exciting progress. In December 2022, scientists at the National Ignition Facility in the U.S. actually achieved a net energy gain from a fusion reaction.
Wait, for real? They got more energy out than they put in.
For the first time ever. It was a huge milestone.
So does that mean fusion power is finally here?
Not so fast. While it was a major scientific breakthrough, the energy gain was very small. And NIF is an experimental facility.
So it's not like we can plug our houses into NIF just yet.
Not quite. Scaling that up to a commercial power plant that can power entire cities is a whole different ballgame.
Okay, so it's a step in the right direction, but we're not there yet. What else is driving all this excitement around fusion?
Advances in other areas like supercomputing and artificial intelligence are playing a big role.
How so?
These technologies allow scientists to design better experiments, analyze data more efficiently, and control the fusion process with much greater precision.
So it's like having a whole new set of tools in the fusion toolbox.
Exactly. It's a very exciting time for fusion research.
So we've got breakthroughs, new technologies, and a lot of uncertainty. Is fusion power really the future of energy, or is it all just hype?
It's still too early to say for sure. The path to commercial fusion power is long and complex, and there's no guarantee of success.
But the potential rewards are huge. If we could crack this, it would change everything.
Imagine a world powered by clean, safe, and practically limitless energy.
It's mind-blowing. But let's not forget about those geopolitical aspects mentioned in that Wikipedia article. Those are some serious concerns.
You're right. As fusion research progresses and commercialization becomes more realistic, there's a risk of a new kind of arms race.
Like countries competing to be the fusion superpower.
Exactly. There are concerns about intellectual property, international regulations, and even the potential for weaponization.
So this isn't just about building a better machine. It's about building a better world to go along with it.
We need to think about the social, economic, and political implications of fusion power right now, not after the technology is already here.
This could be a double-edged sword. The benefits are enormous, but so are the risks. What does this mean for the future of energy? What does it mean for us?
It means we need to be smart and strategic about how we approach fusion power. We need international cooperation, responsible regulation, and a focus on ethical development.
It sounds like the stakes are incredibly high.
They are. The pursuit of fusion energy isn't just about achieving a technological marvel. It's about shaping a better future for all of humanity.
That's a powerful message. It seems like we've only scratched the surface of this topic, but unfortunately, we're out of time for today.
Imagine a world where we don't have to rely on fossil fuels anymore.
No more oil, no more coal.
Exactly. And think about all the pollution that would disappear.
And climate change. Could we actually solve that?
It's possible. If we can make fusion power work, it could be a game changer for the planet.
It's hard to even imagine a world without those constant worries about energy. And what about all the conflict over resources?
That could be a thing of the past, too. With fusion, we wouldn't be fighting over oil or gas anymore.
And it's not just electricity, right?
You're right. Fusion could change so many other industries. Think about desalination. We could use fusion power to turn seawater into fresh water.
Wow. So we could solve water scarcity issues, too.
Exactly, especially in those regions that are already struggling with drought.
That would be incredible. What else could we do with fusion?
Well, think about any industrial process that needs a lot of heat or energy.
Like manufacturing.
Exactly. Fusion could make those processes cleaner and more efficient. It could even lead to whole new ways of making things.
It sounds like fusion could usher in a new era of technological advancement.
Absolutely. It has the potential to transform our world in ways we can barely imagine.
It's pretty mind-blowing. But let's not get ahead of ourselves. We talked about those geopolitical concerns earlier. Could fusion actually become a source of conflict instead of cooperation?
It's a real possibility. We can't ignore that. The development of fusion technology will definitely shift the balance of power in the world.
The countries that control fusion would have a huge advantage.
Exactly. And like with any powerful technology, there's always the risk of someone using it for the wrong reasons.
So it's not just about building a better machine, it's about building a better world to go along with it.
That's the key. We need to make sure that fusion technology is used responsibly and ethically for the benefit of everyone.
It sounds like we have a lot of work to do.
We do, but the potential rewards are so great that it's worth the effort.
Well, we've covered a lot of ground today, from the basic science of fusion to the challenges and the possibilities and even the potential risks.
It's been a fascinating deep dive.
It really has. So what are some key takeaways you hope our listeners will remember from this deep dive?
Well, first, I hope they understand that fusion power has the potential to be a truly revolutionary technology. It could solve some of the biggest problems facing humanity.
Like climate change and energy scarcity.
Exactly. But we also need to be realistic about the challenges ahead. The path to commercial fusion power is still long and uncertain. There's a lot of work to be done.
And as you said earlier, it's not just about scientific progress. It's about making sure that we use this technology wisely and for the good of everyone.
We need international cooperation, responsible innovation, and a strong commitment to using fusion for the betterment of humanity and our planet.
That's a great message to end on. So to all our listeners out there, stay curious, stay informed, and stay engaged with the world around you. And don't forget to like and subscribe to The Deep Dive for more explorations into the fascinating world of science, technology, and beyond. Until next time, keep diving.